Hello everyone, welcome to this lecture number 12 of the NPTEL lecture series on charging infrastructure, and in this lecture we will continue our discussion on single phase boost PFC converter. So if we recap some of the things we have studied in the context of single phase boost PFC converter. So what we have is, we have studied that this boost PFC converter consists of a rectifier at its first stage, then followed by a boost converter which has the input nothing but Vd, where Vd is nothing but the modulus of Vs, and then the switches S1 and S2 are switched at a high switching frequency in such a manner that on an average sense you can apply the variable V converter voltage, and that is when one can control the current which is coming out of the converter in such a manner that this current will be following the same pattern as that of Vd and without having any phase difference. At the same time, this switches need to also switch in such a manner that along with this current being in the same phase as that of the Vd, or this current which is, again you can say that it is a rectified version of the current drawn from the AC input. So this Is current and this Vs is in the unity power factor. So these switches need to operate in such a manner that this Vs and Is is in the unity power factor, as well as the output voltage is controlled within or is regulated within the permissible range of the voltages. So for that we have understood that the duty ratio of this S1 switch, which is nothing but the fraction of the time in the switching period when the switch S1 is on, is nothing but 1 minus Vs peak sin omega t modulus of Vs peak sin omega t by V naught. The inductance, we have again calculated the inductance value, which is nothing but V naught by 4 delta IL max F switching, where F switching is the designer choice. Generally this F switching will be very much greater than the line frequency or the input AC voltage frequency. And the delta IL max is nothing but, again it is the designer's choice, or sometimes it is also given the specification that what could be the maximum ripple in the current one can expect or one can allow in the inductor current. So that will be delta IL max, that will actually determine the value of this inductance, and this V naught is again can be derived from the specifications. Similarly, the capacitance value, this capacitance value sees double line frequency component on the output voltage or on its voltage. That means you have the ripple on that capacitor which has the double line frequency component. Now this is one of the drawback of single phase boost PFC converter or in single phase AC to DC converter in general, and this capacitor, the capacitor need to be sized to actually limit that double line frequency component within the permissible limit, and that requires a good amount of capacitance value, and thus it is one of the bottleneck of single phase AC to DC converters. Again, those converter you are operating in such a manner that it is drawing unity power factor current and able to maintain the output voltage within a permissible voltage range. So this double line frequency component onto the capacitor voltage is one of the drawback, and it is one of the critical aspect which actually determines the size of capacitance, and that will actually determines the overall size of that single phase AC to DC converter. And then we, after understanding the value of L and C, we have started seeing different ratings of the switches, because one also have to select the appropriate switches. So we have for that we are defining the RMS current which will be flowing through the switches, and for that we have seen RMS current flowing through the switches in a very generalized converter case, where which has half bridge and having the current I naught coming out of that half bridge, I mean constant current I naught coming out of that half bridge. So that we have seen, and when the SA is conducted for D fraction of time in a switching period, then we can write down that RMS current of that switch SA, or the current which is flowing through switch SA, is nothing but I naught times under root of D. So this we have derived from very generic voltage source converter which has this half bridge as a fundamental building block, and that particular expression or that particular understanding we have expanded it to this particular S1 switch, and there we saw that IS1 is nothing but under root 1 by T by 2. T by 2, again T is nothing but 1 by Fs, which is, I mean, time period corresponds to the line frequency or the AC input frequency, going from 0 to T by 2, because this the average current which will be flowing through this inductor will repeat itself after T by 2 period, or after half the cycle it will repeats, because if we see the Vd will look like this, and IL, or you can say IL average or ID average, will also look like this, because we are making sure that converter is operating with a unity power factor current, or the current drawn from the AC voltage source will have the same phase as that of the grid voltage. So here this is the average value of you can say ID average or IL average, and the actual current will have something like ripple associated with that. So the current will have the, I mean, you can say that double line frequency component, you can say, which is nothing but this is which repeats itself in T by 2 period. So that's why, since the operation or the operation of circuit will repeat itself after every T by 2 period, so we have taken 1 by T by 2 period going from 0 T by 2 Is square. So here whatever, so whenever in the positive half cycle, whenever this D1 and D4 is forward bias, your Is is nothing but equal to Id. So that's why the same Is will be flowing through the Id, and the same Id will be flowing through the switch S1. So in every switching period the duty is changing, that's when the RMS current flowing through the switch will be varying. So that we have calculated for each cycle, and we are taking the mean over the entire half line cycle. So that's when it is Is square times dt or d of t, and variation, I mean, that is a summation going from 0 to T by 2. So that will give you the RMS current of the switch S1. And then whenever the switch S1 is off, that means S2 is on. So whenever the S2 is on, this entire V0 is coming across this switch S1. So we can say that the voltage rating of this has to be greater than V0, which is generally it is taken as between 40 to 60%, and that is somewhere around 1 point, I mean, if the with some safety margin one can select, let us take 40% safety margin. So the voltage which voltage rating of I mean which you will be using to select the particular device should be at least 1.4 times that of the output voltage which will be there in the converter. Now let us further see our discussion related to switch S2. So for switch S2, in the same line of S1, we can see that this switch S2 conducts only during 1 minus d of Ts duration. That means if Ts is the switching period, so S2 conducts for this much time, and whenever the S2 is off, that means as whenever the S1 is on, then Vs2 has to block the entire V0. If you do in this particular KVL, if you do KVL in this particular loop, whenever the S1 is on, this entire V0 will be appearing across this S2 switch. So that's when Vs2 has to block the V0, and generally we take some with some safety margin. So Vs2 will also be 1.4 times of V0. So that will, generally you select the device for this S2 in such a manner that it should be in a position to block 1.4 times of V0. And let us also calculate the RMS current which will be flowing through this in the same manner as we have calculated for S1 switch. So let us calculate IRMS for S2 switch. Again, this S2 switch will the operation or the current which will be flowing through the S2 switch will repeat itself after T by 2 period. So, we will do T by 2 period, and then the mean we will be taking for 0 to T by 2 period, and in each switching cycle we are actually allow, or we the S2 is actually conducting only for 1 minus d of t fraction of the time of that switching cycle. So, our duty ratio of this S2 switch is nothing but 1 minus d of t, and the current which will be flowing through this one Is during positive half cycle, what we can see that the Is is nothing but equal to Id, and that same Id will be flowing through the S2 switch whenever the S2 switch turns on and S1 turns off. So, we can write down that it is this Is current which is going through the S2 switch, Is of t square times the ratio of the or the time during which this S2 switch is on. So, which is nothing but 1 minus d of t fraction of the time it is been conducting, and then take the root mean square over the entire half line cycle going from 0 to T by 2. It is because the operation of the boost converter, which is the second stage, repeats after every half cycle of the line frequency, that means 50 or 60 hertz. So, that is why we have taken 1 by T by 2. Now, this will define the RMS current. Again, this particular expression one can put the value of d of t, and since we are assuming that the converter is operated with a unity power factor current, so we can write directly 1 by T by 2 nothing but Is peak sin omega t 1 minus d of t is nothing but 1 minus Vs peak sin omega modulo t divided by V naught dt. That one can easily do. Okay, again this is going to 0 to T by 2. So, we can write 0 to T by 2 sin omega t minus sin omega t by V naught, and this has to be integrated over the half line cycle or a half line cycle period. So, then you can calculate this IRMS which will be flowing through this current through this switch S2, and this you can easily put it in some advanced mathematical tools and try it, and you can easily find out the value of this integration. This Vs peak you already know, because once the specification is been given, you know that what is the peak voltage your input can go. So, that you know, because generally RMS of input voltage has been given. So, you from there you can calculate Vs peak, and once the converter specification is given, already the output voltage will already be defined. So, these two things are known. Is peak you can easily calculate by doing or by recalculating the power which will be drawn from the grid from there, since RMS voltage value you already know. So, you can easily calculate the Is peak as well. So, that is how one can easily calculate the current which will be flowing through the S2 switch. One already know the voltage which will be appearing across the S2 switch, already know what is the RMS current which will be flowing through the S2 switch, and thus one can easily select the required device which can be used in this converter. On the similar line, one can also calculate the average current which will be flowing through this switch S2, that also one can calculate, and that will help the designer to select the appropriate switches. So, if you want to calculate I average going through S2 switch, again we have to find the average. So, it is again mean taken over T by 2 period going from 0 to T by 2 period, and here since you have to calculate the average current which will be flowing through this, so you can easily do it by writing 1 minus d of t. So, in each cycle it will be this particular switch will be conducted for 1 minus d of t fraction. So, this will be Is times 1 minus d, and that you have to take an average from 0 to t by 2, and that is when by solving this particular expression, again d of t one can put and Is of t, which we assume that the current drawn from this source is nothing but having a unity power factor. So, this is nothing but Is peak sin omega t having the same phase as that of the grid voltage. So, that is when you can put and you can easily calculate the average current through the switch S2, and accordingly one can select, I mean if one has to select the IGBT, so accordingly based on this current rating, based on average current rating they can select the IGBT. If someone has to select the MOSFET, they can use the RMS current. So that is how one can select the required switches in the boost PFC converter. Now let us try to evaluate how one can select what will be the diode rating one need to select. So let me take for diodes, and again if we see, if we look very carefully, since this diode is having the same functionality as it was there in case of full bridge diode rectifier, where D1 and D4 are forward biased during the positive half cycle and D2 and D3 will be forward biased during the negative half cycle. So thus the concepts what we obtained or what we derived during the discussion of full bridge diode rectifier or uncontrolled rectifier, the same concept will also be following here. So you can write easily that the peak voltage which these devices has to block is nothing but VRRM is nothing but Vs peak, because your VD is nothing but modulus of Vs sin omega t, Vs peak sin omega t, and then whenever the D1 is on, that entire modulus Vs peak sin omega t will be appearing across this D2. So the diode and the same thing will be there in the negative half cycle for D1. So the maximum rating for which the diode need to be sized will be nothing but Vs peak or the peak value of the input sine wave. And similarly one can calculate the forward RMS current. So to do that, in one line cycles, this D1 and D4 will be in conduction from 0 to t by 2 period, while it is not in conduction from t by 2 to t period. So and then again the cycle repeats after one line cycle. So we can just do the forward current nothing but under root 1 by t going from 0 to t by 2, because in t by 2 to t it will be conducting a 0 current, will be nothing but, we can, if we take Is peak sin omega t is the current, we assume that if this current is or having the unity power factor, so we can say that Is peak sin omega t square of that dt. So that one can easily evaluate and they will get nothing but Is peak by 2. That is a forward RMS current of this diode. So that will be used to actually select the diode having required I square T rating. Similarly, one can calculate average or forward average current, which will be nothing but again 1 by T going from 0 to T by 2 Is peak sin omega T dt, and that if one solves it, they will get Is peak by pi. That will be average forward current going through the diode, and accordingly diode rating can be selected. So in this way one can select all the 4 diodes. So we have seen up till now the switches rating, diode rating, the capacitance value, inductance value. Now we have to calculate the RMS current which will be going through this inductor and the RMS current which will be flowing through this capacitor. So let us see in the, maybe in this one, current of capacitor and inductor. So let us first see for inductor. So since the current flowing through the inductor IL is nothing but equal to ID, we can then, and this ID is nothing but equal to Is in positive half cycle, and it is equal to minus Is in negative half cycle. So in magnitude wise, this both this ID and Is are nearly same. So what we can do is we can, and since this is same as IL, so we can write down IL RMS. And now if you see very carefully, this IL will be there, I mean the current through the IL will be always be there, whether it is, whether switch S1 is turned on or whether switch S2 is turned on. And this IL current will repeat itself after every half cycle, or that means after every T by 2 period it repeats itself. So that's why we have taken 1 by T by 2, going from 0 to T by 2, Is square d of t dt plus 0 to t by 2 Is square t 1 minus d of t summation going up to dt. So that if we do addition, what will we get is 1 by t by 2 going from 0 to t by 2 Is of t square into d of t. And if we consider that it is 0, Is of t is nothing but Is peak sin omega t, where one can do, and that will be nothing but Is peak by root 2, that is nothing but RMS current of this inductor. So accordingly, depending upon this RMS current, because we already know Is peak, how one can calculate Is peak. So generally in the specification PL is already given. So one from this PL one can calculate P in is nothing but PL by efficiency of the converter. We can assume one efficiency and then we can easily calculate how much amount of power need to be drawn from the input. And we already know the P in is nothing but Vs peak by root 2 and Is peak by root 2, and that we know that we can easily calculate our Is peak nothing but 2 times P input divided by Vs peak. That's when one can easily calculate Is peak, and from that one can calculate what will be the RMS current will be flowing through the inductor, and that will be useful for actually selecting the wire size of the inductor which will be wounded over the core to obtain the required inductor. So similarly we can also calculate in the similar lines, we can, let us also calculate the RMS current flowing through the capacitor. So we know that for capacitor, let us calculate RMS current. We know that the current which will be flowing out of this the half bridge of this boost converter is nothing but will be going to, some portion will be going to the capacitor and another portion is going to the load. So we can easily calculate this I converter. This I converter is nothing but same as that of the current which will be flowing through the S2. So we can say that I RMS converter is nothing but, I mean this RMS value of this current is nothing but we can change the notation. I RMS of converter is nothing but I RMS of S2, and we know that I converter is nothing but IC plus IL. So the ripple part is going through the IC while the average value will be going through this load RL. So we can calculate I RMS of C is nothing but I RMS of converter square minus IL square, and this particular thing is nothing but same as I RMS of S2, and this we can easily calculate IL value is nothing but V naught by RL, and thus we can calculate what is the RMS current flowing through this capacitor. We can come to conclusion of what will be the current, and thus can easily able to size the capacitor bank. That means parallel combination of capacitor bank one can decide. So till now we have seen all the 4 diode ratings, we have seen all the switches rating, we know what is the value of capacitance, we have also seen the RMS current flowing through the capacitance, we have seen the value of inductance, we have also seen the RMS current flowing through the inductor, and using this information one can select the required component and can build this kind of power converter for the required specification, which includes some information like output voltage, input voltage, output power, and permissible voltage ripple, and what is the AC frequency. Using those information one can easily, and following this procedure one can easily size the component accordingly, and thus can able to build the power converter with the single phase boost PFC converter. Now we will see in the next lecture how to control the functionality of this converter such that we get unity power factor current drawn from the source, and we could able to regulate or control the output voltage at a desired level or at the required level. Thank you for patiently listening to this lecture. We will see you in the next lecture.